Okay, we are going to finish our 6.1 notes today. We got past example 1 and we left off right here where it says randomized comparative experiment. An experiment that compares two treatments. It has a random assignment of patients. That's where we get the randomized word. That's important. One group for each treatment. Groups are in similar size. And the what treatment each group gets and the response variable compared. So those are all parts of the random experiment. Random comparative experiment. So let's say if we were doing our caffeine experiment, I would have randomly assigned you to determine what two groups. One group would have gotten caffeine and one group wouldn't have. So one group for each treatment. Caffeine, non-caffeine, but both have a drink. The groups would be equal in size, randomly split. You have to list what treatment they got, group got caffeine, what group didn't. And then the response variable would have been heart rate, or whatever you're measuring after. Right? A control group is separate from those. It's a group that allows you to control for any effects. It could be a placebo or a group that is receiving an existing treatment. So if we're still talking about that caffeine experiment, the control group would have been a group that drank non-caffeinated soda. So, but it would still have the same amount of sugar as the other one, or no sugar, even better. That would have been a control group. So we'd be comparing everything to that. All right. When you're doing a random comparative experiment, first, randomly assign your subjects. Proper comparative design ensures that influences other than the experimental treatments operate equally in all groups. So if things are perfectly random, the two groups should be equal in things that would affect it. Equal weight, equal height, equal age, equal gender. Anything that could affect the experiment. It all depends on what it is. If we're still talking caffeine, equal pre-consumption of caffeine levels. So like I want half the group of people in my group to be caffeine drinkers and half of them to not, and the same in the other group. Half caffeine drinkers, half not. And if everything is done completely random, that should work itself out. Let's see. Therefore, the differences in the response variable must be due to the effects of the treatment. So doing this like that is to help eliminate those lurking variables. We don't want anything else to affect our results. We want to know, does caffeine influence heart rate? Okay, here are the three principles that you need to remember. Control the effects of lurking variables. Use a comparative design and ensure that the only systematic difference between the groups is the treatment administered. Randomize to get people into those groups. And use enough subjects in each group to reduce chance variation. There's always going to be one person who has a severe reaction to caffeine and their heart rate shoots up. But if we have enough people, that reaction gets averaged out. Okay, turn the situation about online classrooms into an experiment. Give a careful outline in this setting. Now, you're in Google Docs, so you can't draw, so am I. So this is supposed to be like a flow chart, so let's see what we can do here. We start by randomly assigning groups. So if I spell random assignment. Okay, we're going to randomly assign them into the two classes. This is about the online class versus the in-person class. So one group is going to do online. One group is going to do in person, and these were randomly assigned. Let's see if I can insert a line, not a horizontal line. Drawing? No. Okay. Well, they're supposed to be in line from random assignment to online and from random assignment to in person. All right. Then you apply the treatment. or in this case, actually we're going to put it here. So before they were taking their class, they did a pretest. Alright, both groups did a pretest, and then we split them into online and in-person. Alright, they had their semester. So this is where you give your time. 6 months. They both wait 6 months. And then they come back together and we do a post-test. Alright, so this would just be line, 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 line. So randomly assigned 2 groups, an online group and an in-person group. So this kind of identifies the treatment also. How much time they spent there, and then at the end we did a post-test and we compared scores. Alright, so that's a basic outline of a randomized comparative experiment. Okay. Something that is statistically significant is an effect that is so large that it would rarely occur by chance. So if our online people had such a higher learning amount that it couldn't even happen by chance. So it's not just statistical error. At our point, there's no way to quantify that. There's no formula for statistical significance yet. So it's just, if it's too high to have happened by chance. Right? And then we have a comparative study. Observational study that compares two similar groups, measures and adjusts for confounding variables. So that's like an experiment, but there's no treatment involved. So they're actually watching the in-person classes and they're watching the online classes, but they're adjusting for the confounding variables. So they would have adjusted for those pretest scores being different and maybe measured for improvement instead of measured for just average score. Okay, so what we're going to talk about today is you as a class are going to design an experiment for the other stats class. I want to see if people can tell the difference between a generic brand and non-generic brand. Brand name. Thinking cereal. Cereal is cheap. So we're going to come up with the actual details of how to run this experiment, what to do, how much cereal to put in the bowl, whatever we need to do. And then I'm going to go get the cereal, and I'm going to do that experiment by your guidelines on the other class. Okay? I will see you